All right, so we've already talked a little bit about changing rate of reaction. So today we're going to talk about how we express reaction rate. And it's done pretty simply. We're just looking at how much change you have in concentration of one of the substances in the reaction over time. So it could be how fast a reactant, like in this case N2O5, is being used up, or it could be how fast a product, one of these two guys, is being made. So one way to do it, we could describe rate in terms of the increase in concentration of oxygen. So I might have rate shown. I might say that rate equals change in concentration of oxygen over time. And sometimes you'll see the delta T, change in time. Obviously, time is always, changing. So if I say over time or over change in time, it's pretty much the same thing. So this would be something that's increasing over time because oxygen is being produced from time equals 0 until time equals, 5 seconds or 10 seconds or whatever it is. You're going to have an increase in oxygen because oxygen is a product. We could also show it the opposite way. We could say that rate is equal to the change in concentration of N2O5 over time, or change in time. Now this way, because N2O5 is a reactant, we would expect its concentration to be going down because it would be starting high and ending low. So we would have a decrease in the concentration of N2O5. Okay, we can also relate rates of change in two different substances in the equation. So for example, if I wanted to focus on comparing how fast the N2O5 is going away compared to how fast the oxygen is being produced, we just have to look at the coefficients because there are two molecules of N2O5 that are decomposing for every one molecule of oxygen that's being produced. And so what that means is the N2O5 is going to be going down in concentration twice as fast as the oxygen is going up. So because it takes two molecules of this to make one molecule of that. So what we're going to do here is just sort of relate them to each other. And so what I mean by that is I'm going to say that the change in concentration, we'll start with oxygen, it doesn't really matter which one we start with, over time is equal to, and I'm going to leave a little space here before I draw my other little fraction here, change in concentration of N2O5 over time. But right now these two wouldn't actually be equal to each other because, as we just said, because of the coefficient here, the N2O5 is actually disappearing twice as fast as the oxygen is appearing. So to even that out, what I do is I multiply that N2O5 by 1/2. Okay, and so now they would be equal to each other because, yes, this is disappearing twice as fast, but I'm multiplying it by 1/2. We could have also multiplied this side by 2 to set them equal to each other. It's just kind of, that makes just as much sense. It's just not conventionally the way that it's done. We always use a fraction in front of the one that has the larger coefficient. So the other thing that we have to do, the one last thing we have to do to actually make this equal, because we said that this side is actually decreasing in concentration. So this would be a negative change, and this would be a positive change. So the way we truly make these two equal to each other is we actually have to put a negative sign out in front of that. So the change in concentration of oxygen over time is equal to negative 1/2 times the change in concentration of N2O5 over change in time. So it's going away, but we've accounted for that with a negative sign, and it's going away twice as fast, but we've accounted for that with the multiplying by 1/2. Okay, so see if we can figure out this one. We've got a different equation. It's already balanced for us. Write the equation that relates rate of production of NH3 to the rate at which hydrogen is used up. So see if you can do that using the previous example. Okay, so the NH3 is being produced. So we've got change in concentration of NH3 over change in time. And I'm going to set that equal to, again, leave a little space here just in case I need to include a fraction, change in concentration of hydrogen, H2, over time. Alright, so this time we have coefficients in front of both of them. So we have a 2 in front of NH3 and a 3 in front of H2. Now, I know that the NH3 is being produced, so it's going to be a positive change, and the H2 is being used up, so it's going to be a negative change. And what I can do is just basically make my coefficients into fractions here and say that multiply this guy by 1/3, multiply this guy by 1/2, and then also say that this one's going to be the negative of a negative so that it ends up being positive, because this side is going to be positive, right? We're increasing the concentration of NH3. Here we're decreasing the concentration of H2. And by multiplying this one by 1/2 and multiplying this one by 1/3, that's sort of going to equal out the fact that, yeah, this one is being used up about 50% faster than this one is being made because of the 3 and the 2. Okay, and so that's pretty much all we have to do with expressing reaction rate. We'll get into actually calculating some reaction rates in the next thing that we do. But rate laws are our next topic, and this is going to be pretty important to the next lab that we do. So what I've given you there is a balanced equation. Obviously I want you to stop at some point and copy all this down. But you have a balanced equation for a reaction, and then you have this in red here. This is our example of a rate law. In this case it says R equals K times concentration of H2. Well, what does that mean? A rate law simply equates the rate of a reaction, so that's R, to the concentrations of some of the reactants. Sometimes we're going to look at all the reactants, sometimes we're just going to look at one at a time. In this rate law, you can see that we're just looking at hydrogen, even though there's also some NO present in this reaction. Okay, so let's talk about where that rate law came from. Where did we get this? All right, so first of all, this would have to have some data, some experimentation that goes with it. And so let's assume, and you're going to be gathering that data in the lab later on, but for right now, let's just assume the data is given to you. And let's just assume that in an experiment, we find that doubling concentration of H2 doubles reaction rate. Okay, so we have so we're looking at two variables. We're looking at reaction rate and we're looking at concentration of H2. And it looks like if we double one of them, the other one doubles as well. So what kind of relationship does that sound like? Okay, so if we double the H2, the reaction rate doubles. So it sounds like that the rate is proportional to the concentration of hydrogen. And if we look at our equation, our rate law, that's essentially what this is saying. It's saying that rate is equal to, and if you remember back to talking about gases, that lowercase k is just a proportionality constant. Basically, it's just a number, some number that's going to be constant. It's not a universal constant, but it's going to make the statement true. Because if we just said rate equals concentration of hydrogen, that wouldn't be true. The two numbers would not be equal, but they're proportional to each other. And so that, if we multiply the concentration of hydrogen by some constant number, we get the rate. So this statement reads essentially rate is proportional to concentration of hydrogen. Not equal to concentration of hydrogen because we have that K in there. Okay. So I'm going to go ahead and write that here. Rate is proportional to concentration of H2 for this experiment. And again, I'm basing that statement on this data that I have here in green. Okay, so that's where this rate law comes from. Okay, let's say we do a little bit more. And by the way, I should finish this statement. It says, in experiment we find that doubling H2 doubles the reaction rate. If I really want to write a rate law for hydrogen, I have to hold the other reactant constant, right? Because we don't want two variables. So really I should have finished this statement in green by saying if concentration of NO is held constant. Let me go ahead and write that in. If concentration of NO is constant. Because if we don't hold that constant, then we really can't conclude, the relationship between concentration of hydrogen and the rate of the reaction. Okay? But let's say this time we hold hydrogen constant and we look at changing the concentration of NO. All right, so let's write another little statement here based on, and we'll just assume that this is based on some experimental data. Okay, so we'll say holding concentration of hydrogen constant, doubling NO quadruples rate. So what does that mean? Well, essentially what we're saying then, and I can now write a rate law for NO. Rate is proportional to, and again I'm just going to use that lowercase k as a proportionality constant. It's not just proportional to NO, but as NO doubles, R goes up 4 times. So essentially what we're saying is 2 to what power equals 4, right? So of course the conclusion then is, well, it's 2 to the second power, right? So doubling NO, because we're taking this to the second power, is going to result in a rate being quadrupled. It's going up 4 times. Okay, so this would be the rate law with respect to the NO, the nitrogen monoxide. So rate is proportional to the square of concentration of NO. And then the last thing that we can do is actually put them together, because we have 2 rate laws now, right? We have rate is proportional to hydrogen, and we have rate is proportional to the square of NO. So the last thing we'll do is combine the 2. And so now we can say that rate is proportional to, we usually just write them in the order that they show up in the equation. So it's proportional to hydrogen and proportional to the square of NO. And so that's the rate law for the equation, because it has both reactants in it. And so that this is the whole rate law for the equation. Okay, and this way we know that if we want to change the concentration of either of these 2 ingredients, we know how it's going to affect the rate of the reaction. Basically, we can just we'll find the proportionality constant, we'll plug in the concentrations of these 2 things for a given experiment, and we'll know exactly how fast the reaction is going to happen. Okay, so the last thing I want to just finish up with is, it's just kind of a little bit of vocabulary that you'll see sometimes, so I want you to be familiar with it. It's this word order, or reaction order. Basically, sometimes you'll see it written this way. The rate law will be expressed, we'll say rate of reaction, or I'm just going to say reaction is first order. It's going to sound like sort of funny, but it says the reaction is first order with respect to hydrogen. And all that means, first order, it just means that the exponent here is 1. It's not written, but it's implied to be 1, right? So first order with respect to hydrogen. In other words, the rate of the reaction is proportional to the concentration of hydrogen. And then you'll see the reaction is second order with respect to, not respecto, with respect to NO. And so again, that second order just refers to the exponent. So in other words, it's proportional to the square of NO. The other thing is you'll see the reaction is third order overall. And again, this is just language that you'll see. You might encounter this in the lab. You might encounter it in a future class. But basically, it's just a fancy way of saying that, well, it's first order with respect to hydrogen, second order with respect to NO, and you're just literally adding them up. So very, very simple.